This video intends to show the derivation for the kinematic equations. If you have little or no interest in derivations, you can skip this video and go to the next one, which is the results from this one. In this particular case, the equations that we're deriving are only when acceleration is constant. Students make mistakes all the time of using these equations when the acceleration is not constant. Don't do that. These equations will not work. Okay, we start off with acceleration, and what I'm going to do is derive equations to get the velocity and the position. Because acceleration is above velocity, we're going to integrate. That's why we're integrating. Start off with the definition. You always start this way. dv dt, that's the acceleration. The acceleration is a number, and it happens to be a. So the equations will have a in them, and a will be the acceleration that the object has. You separate the variables like you do all the time, so you multiply through by the dt, and on the left-hand side you have dv. On the right-hand side you have a. It's just a number, it's a constant, times dt, and then you integrate both sides. When you integrate that, you end up with this equation right here. Don't forget the plus c. To determine the values of c, what I'm going to do is say that at time equal to, you can think of that as original or whatever. So at time to, the velocity is equal to vo. In your textbook, it always uses t equals 0, v equals v0. But this is a more general case, and there will be a couple of problems that this will come in handy for. So that's the modification. So if you put that in there, for the value of v, you have VO. So VO equals A, T is equal to TO plus C. You solve for C, this is what you get. Okay, so we start off with the velocity. So it's AT plus VO minus A, that's your C. So you just collect up these terms. So you collect up these two terms right here, and they go like this. So it's fairly easy to remember. So all it was is a little algebra there. So this is the concluding equation right there. Okay, now suppose you want position as well. So what we'll do is we'll start off with velocity is equal to the derivative of p, just like always. You're going to separate the variables. This is p. If you notice, this is exactly the same. So we separate the variables, and so you have on the left-hand side the integral of dp. Now on the right-hand side you have this term times the dt, and then you just integrate both sides. So that integral is not too hard to do. v0 is a number, it's a constant, so that's that term. This guy right here, this piece I guess, is equal to 1/2 at squared. And then when you integrate this one, you get this term right here. Okay? And then you add another constant, d. Okay. In order to find that constant, we're going to say when time is equal to TO, position equals PO. And I'm using P instead of X or Y because depending on the problem that you're working, the position variable is sometimes named different things. So I'm just going to use P for position. Okay. So what you do is to evaluate that d, you put in P0 in for P. So this is P0. This is the V0. The T is T0. This term right here comes down here. That's T0 squared. This term comes here. So you get a TO plus the D. So when you solve for D, you throw everything else to the other side. This is what D ends up being. It's just a real simple calculation for D. Okay, so what I did then is I took this term, the P, pull it down here, and your D is right here. This is what we found out that D was. And now I'm just collecting terms up, so I'm going to pull off the P0, and I check it off, got it. Okay, then here's a V0T, and so that would be this term. And there's a V0 minus T0, that's this guy. And then the 1/2 A is right here, 1/2 AT squared, right there. And then there's a minus, if you pull the 1/2 out, it's 2, minus 2AT0T, that's this term. Got that one. And then there's this term that's left over. The 1/2a gets factored out, and you're left with the t0 squared. So if you look at this term with the 1/2a business, that's just the square of the negatives. So this thing will reduce to this one. All right, so that's the second equation that we're going to use. The third one, I'm going to start off by using the chain rule. So I'm sure you've seen this before. V dv d position equals acceleration. And then you separate the variables, integrate. So on the left-hand side you have 1/2 v squared. On the right-hand side you have AP plus C. This time P is equal to P0 when V equals V0. So you substitute that in, solve for C, and then you just simplify things a little bit, and here's what you end up with. V squared minus V0 squared equals 2A position minus position. In your book, I think you'll see it like this. V squared equals V0 squared plus 2AP. They use X in your book, but it's just position, whatever the position is. It's the same thing. Okay, now the other thing that you need to be able to do for this, to work these problems, is you have to know what the accelerations are. Now here's in order to prove this, to derive this, you got to be in chapter 13. So at this point I just ask you to trust me, but I'm sure you've heard that force equals mass times acceleration, Newton's law. So we're going to start with that, and we're going to discuss that in chapter 13. In order to determine the forces, you draw yourself a free body diagram, which I've done here. So this is a body that's in free fall. Nothing is touching it. The gravity is attracting it downward towards the earth, but nothing else is touching it. So the force is down, and it's equal to mg. So we're going to take up to be positive. So now the force is equal to a negative because it's down. And the magnitude of the force is mass times gravity. I don't think that's too much of a mystery for you. According to Newton, that equals mass times acceleration. The masses cancel, and you're left with the acceleration equals a minus g. What this means is that if it's in free fall, if it's in free fall, the acceleration of the object is equal to g, and it's down. This is why the physicist, or whoever it was that named it, called g the acceleration of gravity, because if you're in free fall, the body will accelerate with g, but that's only if it's free fall. Now also the other thing that you need to know is if you sum forces horizontally, if you look at the free body, there's nothing here unless you got wind resistance or something like that. But if you have no wind resistance, there are no forces horizontally. So according to Newton, forces, 0, will have to equal mass times acceleration. In this case, it's the horizontal acceleration. So what we conclude then is that the horizontal acceleration is equal to 0. So in free fall, there is no horizontal acceleration, and there is a vertical acceleration downward equal to g. So those are the things that you need. So that's the end of this derivation.